Okay, my dudes, we're gonna start out with something a bit new for this channel, and we're gonna be talking about some simple calculus that everyone else can learn, because I feel like mathematics is the most important thing in life. And if you can't understand calculus, then how can you understand the vast complexity that is the human experience? So we're gonna start out with a simple definition of what we're gonna be working with. And all we're interested in calculus is how functions change. So we got a simple function. Let's say let's do f of x of x equals x squared. And you have your your 1, 2, 3, 4, and you got 1, 2, negative 1, negative 2. You got 0 goes up to 1, and 2 squared goes up to 4. And you have this. What people want to do as calculus is they want to find the rate of change at any point in the graph. So at any point, let's say x equals 1 comma 1, we want to in calculus be able to find the derivative of that, or the instantaneous rate of change. You're going to find that in physics. So if you zoom in on that little point on that graph, you have your curve. It's always going to be changing, and it's not defined at any point. For example, for the graph of f of x, let's have this thing go negative. F of x equals, instead of x squared, how about instead of that, just make it x, x to the first. You got a simple thing going on, you got your graph, it's going straight up, and if you zoom in on the graph at any point, you're going to see that the graph is always going to be increasing with a rate of change of over a value of 1, it's going to go up by 1 at any point in the graph. You see here, 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 it's always going to be the same. And that changes for graphs that are complicated, like f of x equals x squared, and that's what we're interested in. So we're going to start out with a simple function, and let's get our graph back to function. So you got your function f of x equals x squared. I know it's a shit-tier graph, but honestly, this is shit-tier math. You got your graph, it goes up, and we're looking to define. Let's get a better graph. We're looking to find the derivative, which is the fancy term, of the graph at any point of x. So at any point x, we're going to find the instantaneous rate of change of the function. So how we do that is quite intelligent. So let's get an actual graph going up here. We have let's get some lines. So you got this, and you got this. Here's your function. Let's get a curve going on here. Oopsies. Let's define it from here. Let's have the stretch down here. Shit. I almost had it good. Say this is f of x squared. So I want to be able to zoom in on any point of the graph. Any point of the graph, and be able to find how this graph is changing on any change in x. So we want to know how graphs work, and it's easy. You can find a secant line. Let's say that this is say right here, this is negative 2. Let's get a good negative 2 in there. Negative 2. We all know that the graph of x of x, or f of x, or f of x equals x squared, it's going to be 4 up here. So you do your classic, your rise over your run, you get 4 over negative 2. And let's have it from this point to that point. It goes 2. We're interested in magnitude. You know what? Scratch that for a sec. Except for the 4. This is a really bad integral. Just forget about that. We're bringing it over. Bring it over to here. Because I don't like negative numbers. They turn out to be real dicks. So you got your thing. You got 2, you got 4. It goes over 2. Then it goes up 4. You got yourself a simple 2 over 4 or 1 over 2. That's simple. You see, you have your secant line from this point. You got your fancy pants hypotenuse, and you're gonna find that the secant line has a slope 1/2, and that's fine when you're working with numbers like 2 and 4. But when you're getting into instantaneous rate of change, that's really when the x is changing by a really small number, 0.0, technically infinitesimally small, and we're looking at the change in y at that point. So you could try at any point of the function. You could try zooming in really far, and there is a rule that the further in that you zoom, the more linear a function will appear. As you can see, once you zoom in a really far bit, you can see that this function looks quite linear, and we're going to see that pattern a lot the more that you zoom in. But we need rules. So let's start with a simple rule. Define the instantaneous rate of change, which we're looking at rate of change when, let's say, change in the function, let's call it a at any point a, and this is the point f of a. Let's get our function up here. Fx equals x squared. Basically, we have this change in x, and we have the change in y, and we have this point, which is right here, a comma f of a, and then you have point well, if this is changed, I don't like this. I'm gonna rewrite that. You got your point, let's say this is point x. Let's define our points. Cover our butts. Yeah, point x. Point x comma f of x. And then this is your change, which is a, and that's your change in y. So then you got point x plus a comma f of x plus a. So we're looking to find this as a gets to a really small number, because as a gets smaller and smaller and smaller, you're zooming in closer and closer and closer, and that's how you're going to find your instantaneous rate of change. It's a trend, you could say. So we're looking at that as a goes to 0. And it's approaching 0. It's not when a is equal to 0. So we can define this as just a series of secant lines that are approaching a tangent line to the value at that number. And that's really all that derivatives are, is that it's just a tangent line, which is the instantaneous rate of change. So you can see a tangent line at point A. It's not necessarily a tangent line at point B. It's pretty easy to understand, so it can change at any point x. So to find that, we're looking at the limit of the function. Let's get my brush back. Let's get some more area to work with. Looking at the limit as a goes to 0, and this is just the equation for a secant line. So you have change in x over change in y. Then you got your x. So the change in x is always going to be a, and then the change in x is going to be f of x plus a, and you subtract the starting point minus x, or f, it's not f of x plus a, it's x plus a. X plus, what am I doing? It's change in y. So you have f, what the fuck am I doing? F of x plus a. Get me out of here. Get a new math teacher. I got f of x. So you have your change in y, which is this minus this, and change in x, which is going to be a, as we said before. So we're looking at limits. And if you don't understand limits, if you get 2 likes, we're going to do limits. And I'm going to assume you guys know how to do limits. So we're going to evaluate this for the function of f of x equals x squared. So let's fill in our shit. So you have the limit as a goes to 0 of, and we're looking at f of x plus a. And you know f of x equals x squared. So you're looking at f of x plus a equals x plus a squared minus x squared over a as a goes to 0. So if you notice, you see why this stuff gets tricky. Because as a goes to 0, you get this mumbo jumbo, you get x squared minus x squared, which is 0 over 0, which is it's a pathology. It's an indeterminate form. And basically we have to fuck with indeterminate forms if we want to get anything good out of it. So we have to evaluate the function. So we can do something pretty simple. We could do the classic, we could just simplify the function so you get x squared plus 2ax plus a squared, you know, simple squaring numbers, minus x squared over a. And that's the same thing. It's just the same limit as a goes to 0 of this function. So if you let a go to 0, you notice that the x squares cancel out. And you get 2ax plus a squared over a. And you know, that's it's a dumb thing because you get 0 plus 0 over 0. Again, you're working with dumb stuff. So let's still keep it pretty simple. We can factor out an a here. We got a times 2x from this, 2x, and then you add the a over a. And you know, if you multiply something and then divide by something, all you really have is something. So you got 2x plus a, and that is the limit as a goes to 0 of 2x plus a. So you let a go to 0, and you notice, well, we dug ourselves out of the shithole, and now you just got 2x, and that baby right there, 2x. In fact, let's get it in pink. 2x is equal to the derivative, and we're gonna use some fancy terms here. Turn out to get too spooked. Let's call it f prime of x, or we'll call it or dy dx. That's useful for differentials. Keep that in mind. Just put that in your back pocket in your suitcase. So now you're thinking, well, what does that mean? That means that at any point of the function x, then the change in y at the instantaneous rate of change of the function at that point is equal to 2 times whatever it is. So if we clear this graph out, let's get a nice sweeping clear here. Let's get some nice beautiful space to work. I mean, if we get some nice beautiful space to work with here. One moment, please. Thank you. We got some nice space to work with here. Let's get our set of axes going up. You got your x and a. And then you got your function of x, which looks something like this. Penis. It looks something like this. And you zoom in on the graph. Why is this so hard? MS Paint. Always make sure to tip your math teachers. If you zoom in at any point of x, let's say x is equal to 2, and you know that 2 squared is equal to 4. Let's say fx equal x squared, and you know fx squared equals 4. Then we know that as we zoom in on this point, the tangent line to this function, the slope of that, is going to be the derivative of the function at that point. And we already figured out that the derivative, or dy dx is equal to x. And we know x is equal to 2, so we know that dy over dx is equal to 4. And that is the rate of change of the function at that point. Super simple, right? You know that the line of this is going to be always forever. It's always going to be, what, ratio 4 over 2 or 2 over 1. It's basically the slope of a tangent line as you have, let's say you're evaluating the function at this point. It's, you could evaluate as all the secant lines converging and converging and converging into that, into one unknown tangent line, which you can figure out. It's just instantaneous rate of change, you know? Tangent line at x equals 0, it's going to be 0. You see? Just draw a tangent line. Tangent lines are super easy, but you're not going to get exact calculations out of them most of the time. If you had a different thing. Let's say if it was 3 over 2, and you went to like the function at like 12. No. At 8. It would be different. I guarantee. And that's what's so important. So you have like a couple of rules for this stuff. You got rules. That's how you do it. So if we do something a bit different, like so you have your set of axes right here, and you're gonna delete it. So you have a set of axes, and you're gonna do a really funky graph, like let's say graph of x cubed. And x cubed looks weird, but it's a special. It looks kind of like that, kinda, you know, except I drew it backwards. Just imagine like this is flipped, you know. You got there's 1, there's -1. Yeah, f of x cubed. We can go back to our rule, which says limit as a goes to 0 of f of x plus I and all that shit, which is really just x plus a cubed minus x cubed over a. And you can see that this stuff is going to get really tedious. So there are a couple rules, and I'll teach you some of them hella quick because they're not fun. They're easy to look up. So we know that the derivative of a constant, let's say that if it was a graph of where f of x is equal to like 1, and you have the straight line here, we know that derivative of a constant, let's put this as derivative of a constant, is always going to be equal to 0, because you're not getting much change in that graph over x. And we also know that the derivative of x, just on its own, is going to be equal to 1, because you know that as the graph goes up, it's constantly going to increase. But for every 1 over you go, it's going to go 1 up. For every 2 over, 2 up. 4 over, 4 up. That's just the rule. That's pretty simple. And but now I can get into a couple more complex rules. Like, let's delete this all. The derivative of a constant times x. So let's say you have the function 2x. The derivative of that is going to be, let's get my thing. It's going to be, let's say, constant times x, and that's not c of x. Constant times x, the derivative of that is going to be equal to the constant. So the derivative of 2x for every 1 over is always going to go 2 up. That's just how it works. And this is where it gets interesting. So let's say we have the derivative of more things. Let's say f of x is equal to f of x is something like 2x minus 4x squared plus 3. And the derivative of that, of that is equal to the derivative of each thing added together. So you could consider that f of x is equal to, say, g of x, where g of x is equal to 2x, minus h of x, where h of x is equal to 4x squared minus 3. The derivative of anything is equal to, or the derivative of the function g of x plus h of x, until you, like, for it can add up a lot, is equal to the derivative of each part. So the derivative of g of x plus derivative of h of x. And if we use this as we learned before, and I know you guys are going to think this is easy. F of x is equal to 2x plus 3x, and you could say, Ryan, don't be a fool. You know that 2x plus 3x equals 5x. But you can use a rule, and you know that since the derivative of a constant times x is equal to the constant, then you know that the derivative of the sum of two numbers is equal to the sum of their derivatives. You know that the derivative of that is equal to 2, and 2 constant, like 2 times a variable, is equal to the constant. That's the derivative, plus 3. And let's do one more thing before I cap it off. Don't want to get too complicated. Gotta get more feedback. Make sure that the students in the back, Jeffrey, he's playing Minecraft on his phone. You should stop. Gotta make sure that your kids are paying attention. Let's get one more rule. Say derivative of an x to a power n is equal to n times x to the power n minus 1 and plus derivative of x. And in most cases, derivative of x, if x is something simple, it's going to be 1. Or sorry, did I say plus? What a fool. I meant times. It should be times dx. So for our function earlier, our f of x equals x squared. If you recall, you know that derivative of that in terms of x is equal to 2x. If we knew this rule earlier, we could just say, okay, well, this is the function of a x to a power. So you have the power times x to the power minus 1, so 2 minus 1, which is equal to 1, times derivative of x, and we know that derivative of x is equal to 1. And that's basically what we did. What we did before was a long drawn-out way. We have a couple of shortcuts. It's really simple, and that works for any power. And what you have to worry about is the chain rule. And that's when you're talking about it's not the derivative of x to the 1, it's the derivative of u to the 1, where u could be anything. So let's say chain rule states for exponents, the derivative of y in terms of x of the function u to the n. It's not that simple. It's equal to, as we remember, n times u to the n minus 1 times du dx. And this is what the chain rule is. Let's get to it. Let's get a clean slate. This is what you need to know. Basically, this could be where u is something different. So when we're working with the function, let's say x plus 1 squared. Actually, that's not a good example. Say 2x, that value squared. You can't just do the simple derivative of x to a power, because it's not x, it's u. It's not simple x, it's something different. Where u is 2x, I didn't mean to circle just 2. Where u is 2x, there's u, and n is equal to 2. You could change anything. Like you could have x or u be a flippity flop to the whatever. Or something like 5x minus like 2 times the square root of like x plus 3 over like 1,000,000,000. And you have that going to the power of like 1 over x. You see, it's not that simple. It's not derivative of x. It's derivative of u, where u is 5x minus 2 times blah, 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 blah. So let's go back to the simple example of, let's clear this stuff out, don't say that shit. Simple example of 2x, that quantity to the third. We have our n, we have our u, and we can use our formula. So we have 3 times u, which is 2x to the power n minus 1, so 2, times the derivative of u. And we know that the derivative of the constant, which is 2, times x is equal to the constant times 2. So the derivative of the function 2x cubed, make sure to put the parentheses around the 2x, otherwise it'll be 2 times x cubed, and that'll change your answer. The derivative of that is equal to, well, 3 times 2 times 2, which is 12 times, actually, pardon me, should be 6 times 2x squared. And that should be like 2 squared times x squared, which is like 24 x squared. Yeah. That's the derivative of 2x to the third. That's it. So yeah, that's math. Here's a triangle. Wow.